Okay, notoriously confusing topic, but again, like some other ones, I think the terminology is what scares people off, as opposed to the actual concept itself. So if you have not watched the videos on force, I suggest that you watch that first because you need to have concept of inertia, of momentum. So watch those two videos, the force 2.1 and the momentum videos first. If you understand those two concepts, then this one should be pretty self-explanatory. The only difference from momentum to angular momentum is we're talking about a rotational or angular motion, right? So moving around an axis, something spinning, something rotating around a bar, okay? A baseball bat swinging around the axis of a person's wrist, okay? These are all examples of angular motion. So angular momentum is the same as linear, only just in this context. Okay, so when rotating a baseball bat, angular momentum can be increased by increasing the mass of the bat. Okay, so like inertia. So if you remember the concept of inertia, the lot more mass it has, the more inertia it has. Okay, well, likewise, the more mass that a bat has, the more inertia it's going to have, the more momentum it's going to have. Okay, you can also increase the length of the bat. Okay, so if the bat is longer, that increases the distance the weight is distributed. So basically, the end of the bat is going to be traveling faster because its range of motion is going to be more. Okay, so again, if it's traveling faster, same as regular momentum, it's going to have more momentum. Okay, so there's this concept of moment of inertia, which I've already started to explain to you, and angular velocity. So angular velocity, like linear velocity, is a speed at which something is rotating, okay, as opposed to speed in which something is traveling. Okay, so rather than talking in meters per second, it's talking degrees per second because it's rotating. So that's what it's measured in. Okay, but otherwise it's the same concept. And the moment of inertia, it measures an object's resistance to change in its angular rotation. Okay, so again, this is the same. Okay, same concept as inertia, only talking about rotational movements. We're going to look at some examples if you're still a little bit confused. But the further from an axis that the mass is distributed, okay, the higher the amount of inertia. Okay, so the bigger the radius, now if you've done maths before, I'm sure you've heard of radius. And when we talk about circumference and radius, the bigger the radius of a circle, okay, then at the end of the outside tip of that circle is going to have a larger range of motion, okay? And if the weight is out there, that means it's going to be going faster and therefore have more momentum. All right, we can work out the moment of inertia, which is just talking about how much inertia an object in angular motion has, can be calculated by the mass times by the radius. So the mass of that object times by how far away from the axis that object reaches. Okay, so here's an example. All right, we have a boy, same boy, same everything, same amount of force, same velocity. The only thing that is changing is the mass of the bat. Not even the mass of the bat is changing technically, the distribution of mass. Okay, so where is the mass is what has changed. Okay, because if you look in the one on the left-hand side, the mass is at the opposite end of the bat. Okay, as the opposite ends as his hands. Okay, when we look at the picture on the right, he's holding the wrong side of the bat. Well, what that means is that most of the mass is going to be right where the axis is. Okay, so what effect does that have? Well, if we increase the moment of inertia because the mass is further away, okay, so if the mass is further away, then the moment of inertia has been increased, okay? Then increasing the moment of inertia is also going to increase the angular momentum. So this bat is going to have more momentum because the weight is further away from the axis. So when it's swinging, it doesn't want to stop swinging, okay, which is what inertia principle is. Okay, so it has more momentum. Okay, likewise, if we decrease the moment of inertia, so the weight is closer, so its radius, the weight radius is closer to the axis, which is his hands in this example. Okay, if we decrease the weight on the end, okay, then it has less moment of inertia. So decreasing the moment of inertia decreases the angular momentum. All right, if you increase the angular velocity, okay, you can also increase something's momentum. So this is why the longer a lever, or in this case, just a radius is, so if the circle is where our pivot point is, so using the baseball example, our hands, if this is where our hands are, and this is where the weight is distributed, okay, then when it gets all the way around to point B, okay, it's traveled quite far, okay, because it has an increased range of motion. If the mass, like in the when the bat was turned the wrong way around, was in here, okay, then the mass only has to move that far. So it has less momentum because it has less velocity. Okay, its velocity is smaller. It's not going as far in the same amount of time. This is going much further in the same amount of time. So its speed is increased out here. Okay, and because the speed is increased, the momentum is increased also. All right, now when we're looking at angular momentum and how we can manipulate it, the closer the mass is to an axis, the easier the object can rotate. So we just said before that this will be going faster, but it doesn't mean it's easier. It just means it's going to have more momentum, okay? When we're looking at the ability to spin, you're going to be able to spin a lot easier when your mass is close to the axis. And in this case, the axis is his center of gravity, which would be around here, okay? So right on the sort of cusp of his belly button, I would say, okay? And if he wants to rotate, which I'll show you in the next slide, decreasing his moment of inertia will make it easier because there'll be less resistance. Remember, that's what inertia is. If you have more inertia, you're going to be more resistant to change in motion. Okay, so in decreasing the inertia, it's decreasing the resistance to change in motion. So it's going to be easier for them to rotate angularly, okay, if they have a smaller moment of inertia. So let's have a look at here. You can get a good idea. So because this person have a decreased moment of inertia, okay, there's less resistance to motion, so therefore they can rotate faster. They have a faster angular velocity. If I go over to C, okay, my radius being the middle point to an end point, my radius has increased. That means my moment of inertia has increased. Right? And if my moment of inertia has increased and my mass has stayed the same, okay, then I'm actually going to have a slower, more inertia. And more inertia means I'm going to have more resistance. So it's going to be harder for me to rotate because I have more resistance to that rotation. The inertia doesn't want to change what it's doing. So lowest moment of inertia, highest moment of inertia. Okay. Now, increasing angular momentum. When rotating a baseball bat, angular momentum can be increased by increasing the mass of the bat as well as the length. Whereas if I want to decrease angular momentum, modified equipment making making a bat smaller will reduce its moment of inertia. Okay. So it makes it easier to change it. All right. But like what happens with inertia, once an object is moving, it's harder to stop. Okay. When an object is stationary, it's harder to move. So if there's less inertia or moment of inertia, okay, then it's easier for the person to move that bat. Okay. So promoting the ability to move the equipment with more ease. All right. The one sort of concept that you need to understand is the same as the conservation of momentum. We have the conservation of angular momentum. So you would have seen a pendulum like this before. It's called Newton's cradle. But basically, if I lift up this far left ball and drop it, all right, there is a huge amount of momentum in this ball, and all the other balls are stationary. Okay. However, once this ball hits this one, it's angular rotation, right? This ball hits this ball, which hits this ball, which hits this ball, and this will go up by the exact same amount. Okay. So you may remember from the conservation of momentum that the total amount of momentum before a collision is the same before as it is after, the same amount of momentum. So this is the same with the conservation of angular momentum. This ball, if I lift it up to here, the law of conservation of angular momentum says that when I let go, this momentum is transferred, then this ball should lift by equally the same height. And that is the case. Now, this is something that confuses people and something that gets asked about. But what you have to firstly recognize is when someone's doing a somersault, okay, there is a change in their moment of inertia when they open up and when they tuck in, okay? As you can see, when they're open here, like in this first top picture of the guy jumping, they have a high moment of inertia. That's because they have a high radius. Their radius is very long, okay? So their moment of inertia is quite high, right? As he wants to rotate, he's rotating through. When it starts to dip, because his moment of inertia is getting smaller, okay, his radius is getting smaller, and it gets at its lowest point when he's tucked into a ball in the middle, because his radius is the smallest. All right, his radius is the smallest, and then as he starts to open up again, he's increasing his radius and therefore increasing his moment of inertia. And as you can see, the moment of inertia at the start is equal to the moment of inertia as it was at the end. Okay. When I look at the angular velocity, so the speed at which he's rotating, you could probably work out that when someone's open like this, his rotational speed is low, okay, because his moment of inertia is high. There's a reluctance to change in the angular rotation, okay? But as his moment of inertia decreases, as he starts to squash into a little ball, the speed at which he rotates around starts to increase. And you can see that his peak angular velocity is exactly in line with his smallest moment of inertia. So when he's tucked in the smallest, he is able to rotate the fastest. His angular velocity is the highest. And then that angular velocity starts to dip again when he starts to open up again because his moment of inertia has increased. And it finishes exactly where it starts, low, because his moment of inertia is high there. Okay? So you can see the relationship between moment of inertia and angular velocity in a diver. Okay, by decreasing the radius of rotation, which makes up the moment of inertia, you're increasing the angular velocity. So when you tuck up in a ball, you can rotate faster. Okay, and that decreases your moment of inertia when you tuck up into a ball. You have a smaller resistance to change your angular rotation, and that causes you to rotate faster. Okay, when you increase the radius of rotation, so when you make yourself tall and the radius is long, okay, like in a pie, it decreases the angular velocity. It makes you spin slower. And this causes you to rotate much slower. Okay, so that's the relationship. As moment of inertia is high, angular velocity is low, right? And when they start to cross over, it is because the person is tucked into a ball, which means there's less resistance to their rotation and they're able to spin at a higher angular velocity. Okay, and this would be the case until they start to increase their body shape, which is increasing their radius of rotation. All right, I mean their radius from the axis, and makes their moment of inertia high again, which in uh, doing so decreases the angular velocity. I think what we need to point out as well is that while this is happening, the overall angular momentum is exactly the same. Okay, yes, the angular velocity is changing, and yes, the moment of inertia is changing, but overall, there is the exact same amount of momentum split between those two things throughout. Okay, that's why there's this straight line here. It's showing that the overall angular momentum during a somersault does not change. It's the moment of inertia and the angular velocities that changes, but the sum of those two is exactly the same throughout. So here is another good video to watch on that. I hope that concept makes sense to you. Please shoot me an email, as always, if you have a little bit more questions or things that you'd like me to go through.